Hello everyone, and today we talk about section 4.1, vectors in Rn. Now, a brief comment on notation. So unless stated otherwise, all vectors are going to be column vectors. Okay, so that's even if you see it written as 1, 2, 3, where it's a horizontal or without the pointed brackets. Okay, that's just going to be to save space. Okay, and I will be guilty of that too. So just understand them to be column vectors. Now, what is Rn? Okay, well, we can first talk about what is R2. Okay, R2 is the R means real, and the 2 means the number of components that vector has. So it's a set of all vectors with 2 components, both of which are real numbers. So 2 is a real number, 1's a real number. There are 2 slots in this vector. This is a vector that's in R2. So 0, 3, negative 1, 1, those are all examples. What's R3? Well, it's the same thing, except there's 3 components to the vector. Okay, so you have an example like the vector 1, 2, 3. Now remember, this is a column vector, even though it's written this way. Or negative 1, 0, pi, because pi is a real number as well. Okay, so take a stab at what Rn is. Okay, well, it's the set of all vectors with n components, okay, each of which are real numbers. Now, for reasons that will become clear a little bit later, okay, linear combinations will be incredibly important to us. Okay, so I give you a vector x that is negative 1, negative 4, and a vector y that is negative 5, 1. And I ask you to compute 3x minus 4y. Okay, it's a very simple task. You probably already know how to do it. Okay, but this right here is, this is a vector. This is a linear combination of the vectors x and y. So linear combination is a scalar times a vector plus or minus scalar times a vector plus or minus scalar times a vector, no matter how many vectors you have. In this case, we only have 2, so it's kind of a boring example. Okay, but that's what a linear combination is. It's a scalar times a vector plus or minus a scalar times a vector, and so on for as many vectors as you have. Okay, so what is this vector v? Okay, this is going to be 3 times negative 1, negative 4, minus 4 times negative 5, 1. So this is negative 3, negative 12, minus negative 24. So what do we get this to be? Negative 3 minus a negative 20. That's going to be, what, 17? Something like that. And negative 12 minus 4, that's going to be negative 16. All right, so that's the linear combination of the vector v. Or that's a vector v, that's the linear combination of x and y. And just to be clear, linear combination is any scalar, not just 3 and 4. Okay, you probably already knew that. So the examples that will be a little bit more relevant to us, okay, I want to express negative 3, 5, 9 as a linear combination of the vectors 1, 0, 2 and 0, 1, 3. So in other words, what we're saying here is some vector, or some scalar, call it A, times 1, 0, 2, plus some scalar B times the vector 0, 1, 3, sums to negative 3, 5, 9. what are those two scalars that do that? Well, that's easy. On the left-hand side, we have a times 1 plus b times 0. So a times 1 plus b times 0. A times 0 plus b times 1. And 2 times a plus 3 times b is how you combine the left-hand side, and all of that's going to be equal to negative 3, 5, 9. So component-wise, you see that a has to be equal to negative 3, b has to be equal to 5, and to verify this works, does 2 times a, 2 times negative 3 plus 3 times 5, question mark, equal 9. Is 9 minus 6 plus 15 9? Of course it is. So the linear combination that we are looking for is negative 3 times 102 plus 5 times 013 is equal to negative 3, 5, 9. Okay, let's look at one that's a little bit harder. Same setup here. Okay, express 11, 7, 5 as a linear combo of the vectors 4, 5, negative 2 plus, and 1, negative 1, 3. Let's see what we get here. So a times 4, 5, negative 2 plus b times 1, negative 1, 3 is equal to 11, 7, and 5. Doing the same thing, okay, combining the left-hand side as a single vector, we get 4a plus b, 5a minus b, and minus 2a plus 3b. And all of that is supposed to equal 11, 7, and 5. Okay, what we have here is the equivalent of a system of equations, 3 equations and 2 unknowns. Okay, so all we have to do is solve this system. You can do it any which way you want. Okay, what I would like to do, because I see a plus b and a minus b, is I'd like to take the top 2 equations, 4a plus b, 5a minus b, and that equals 11 and 7 respectively, and add those 2 equations together. I get 9a plus 0 is equal to 18. So turns out that a is equal to 2. If a is equal to 2, and I know that 5a minus b is equal to 7, that means, so that implies, that's what that symbol means, that 5 times 2 minus b is equal to 7. So that's 10 minus b is equal to 7. So we know that b is equal to 3. Okay, that is not yet my answer. Okay, those are the values of a and b that make the top 2 equations true. What I need to do is I need to confirm that it satisfies the third equation, because if a equals 2 and b equals 3 makes the top 2 equations true but not the third, then I don't have a solution. So let's verify that. I'll verify it in a different color. So taking this equation right here, I get minus 2 times what? 2 plus 3 times 3 is equal to 5, and that's minus 4 plus 9 is 5, and that's a true statement, so that works. Fantastic. So I can say that 2 times 4, 5, 2, that's negative 2 actually, plus 3 times 1, negative 1, 3 is equal to 11, 7, and 5. And so that is the linear combination of the given vectors that produces 11, 7, 5. Now, what would happen if the third equation, the thing that's in red, wasn't true? Okay, well, there would be no such linear combination of vectors 4, 5, and 2, 4, 5, negative 2, and 1, negative 1, 3 that produced 11, 7, and 5. And that's perfectly fine. There doesn't have to be. Okay, so that would just mean the system of equations was inconsistent and no solution exists, and that's good to know as well. Okay, but to answer the question that was presented, this is the linear combination of the vectors that produces 11, 7, and 5. So that's all I need to get you through, started in section 4.1. This is a quick video. I'll give you another one for section 4.2 in just a little bit. And things will start becoming a little more interesting. We'll be dealing with stuff that you have not seen beginning in section 4.3. Take care, and I hope you're having a good day.